Electric power was introduced as the clean, modern route to the future. Now it's entered so many aspects of our lives, modern civilization could barely get along without it. Think of what your day would be like without electric power. Electric power must be precisely controlled, not just because of its own value, but because we usually use electric power to control other forms of power. Like mechanical and fluid power, electrical power is the rate of doing work. Or work divided by time. But instead of the work of moving objects or fluids, electric power is the rate of moving electric charge. Electric work is done by voltage moving coulombs of charge. To turn that into power, we simply put that work over time. But does this look familiar? Q over T, or quantity of charge moved in a period of time, is a rate. We saw in our rate unit that a coulomb of charge moving through a wire in 1 second is 1 ampere. Isn't it convenient that an ampere is a rate? That means that we can more conveniently use our second formula for calculating power. Force times rate. Voltage is the force, amperes or current is the rate. In other words, a volt times an amp is electric power. Electric power is expressed in watts, named in honor of our friend James Watt. The wattage rating on a device tells us the amount of electric power it consumes. The meter on the side of a house shows the power consumption of the building. The wheel in the center of the meter runs at different speeds depending on the amount of power being used by things like appliances and electric heaters. The faster that wheel spins, the more power is being consumed. In other words, the faster the wheel spins, the faster the money goes out the door. The gauges measure the watts of power by the thousand, or kilowatts. The power companies are not just interested in kilowatts of power being used by all the appliances in the house, but also how long that power is used. So the meter is also measuring time, or the number of kilowatt hours. You'll be dealing with this meter in more detail in your laboratories. Power companies must constantly change their power outputs as the demand changes. Every day there are 2 electric rush hours, one in the morning and one in the evening when people turn on all their electric appliances to cook meals, usually at the same time. The power into a device is only half the story. If we also measure the power out, we measure efficiency. This is an important consideration because some devices, like a laser, are not very good.
Well, what you see in front of me here is an argon laser, and it's a gas laser, and it's water cooled. Now, lasers of this type require a lot of power, a lot of electricity, and they're very inefficient. What that means is this laser will require about 20,000 watts of electricity for about 1 watt of laser light out. So that means about 20,000 watts of power has to be dissipated by the water cooling. So what happens is the electricity comes across the tube at the 2 ends and heats it up, and the water cooling is wrapped around in coils that go from the back of the laser towards the front. So by wrapping in coils like this, it does pretty much sufficiently cool the laser.
Usually electric power is turned into some other form of power. In this case, it's light and thermal power. Very often, it's turned into rotational mechanical power of turning a shaft. If we want to measure the efficiency of a motor like this, we have to compare the mechanical power out to the electrical power in. Fortunately, Mr. Watt made that easy for us. Remember that James Watt calculated a mechanical watt as a joule per second. But the joule is also a unit in the electrical system, so we can easily convert from mechanical watts to electrical watts. In fact, they even have the same value. We can even go further than that and compare electrical watts to horsepower. It turns out that 1 horsepower is equal to about 746 watts of electrical power. By comparing electric power to other forms of power, we're able to match electrically operated devices to specific jobs. Electric motors are good for heavy loads because they're self-starting. There's no need for clutches and transmissions. They're also capable of tremendous speeds. The fastest trains in the world are electric. The main limitation is how much power can be delivered to the vehicle. By the way, if you'd like to see a precise control of voltage and current, both the opening title of this program and these effects were done by the laser you just saw.